Hello there, and welcome back to the course summary of EE2015 Electrical Circuits and Networks. And in the last video, we just discussed nodal analysis and its implementation using uh, the Kirchhoff's current law. And this is a continuation of the same video. That is, here we'll be discussing loop analysis. Loop analysis is fundamentally based on Kirchhoff's voltage law. That is, energy is neither destroyed nor created when you go through a closed loop in an electrical circuit. And let's see how it can be applied to our circuit. So here is an example that will help us understand this quickly. So as you can see, there is a network of resistors and a couple of voltage sources, and uh, this approach is by assuming a current, let's say I1, I2 and I3 in each of the loops, such that the net current through, let's say, R12 will be equal to I1 minus I2 or I2 minus I1. So as you can see, the current through R1 is not simply I1 or I2, it is a combination of both of them. And now we can also see that the current directions are all in the same way. They are taken clockwise here. This will make our understanding easier and equations more easier to apply. So let's try to let's try to understand the application of the voltage law in, let's say, mesh 1. So mesh 1, let's start with V1. So when we start from V1, there is a potential gain of V1, so plus V1. And when we go through R11, there should be a potential drop of I1 times R11, that is V1 plus V1 minus R11 times I1. And then going ahead in the loop R13, the net current through it is I1 minus I3. So the potential drop will be R13 times I1 minus I3. At this point, I should say that the couple of equations written on the upper right corner for labeled as M1 and M2, those are only considering I1 and ignoring I2 and I3. To see the overall picture, you can please, I request you to ignore the couple of equations to avoid confusion. The main equations have been written below the diagram. We'll come to the rearrangement later. And later in the mesh 1, we have R12, and net current through it is I1 minus I2. So the potential drop again will be R12 times I1 minus I2. And this total energy should be equal to 0. So on rearranging this term, we will get R13 times I1 minus I3 plus R2 times I1 minus I2 plus R11 times I1, that is equal to V1, just as we just said. So writing similar equations for mesh 3 and mesh 2, we'll get the couple of equations written over here. Again, on rearranging the terms such that we get coefficients of I1 together, I2 and I3, we'll get something like this, which we just saw for the nodal analysis as well. And again, these equations can be represented as a matrix in I1, I2, I3, the current vector and voltage vector. And this is a resistance matrix. So resistance matrix, when we take an inverse and multiply on both sides, we'll get the currents directly, I1, I2 and I3. And once we get the currents, we can find the current and voltage across any branch, any node on this circuit. So that's how it works. Again, one can see that what if there are current sources as well. So when there are current sources, we can use the same approach we used for voltage sources appearing in the nodal analysis. That is, we can assume an arbitrary, let's say an unknown variable, Vx, potential difference across the current source, and we'll have one more equation to solve the circuit, as you can see in an example given over here. That is, there is a constant current source, and we have assumed a potential difference across it. That will give us one more equation, and that is I2 minus I1, that is will be equal to I1 minus I2 is Is, and these equations will be ready for us. So that's how loop analysis goes. I hope this made it very clear how the loops and matrices work. In the next videos, we'll try to understand few more circuit theorems that will make our understanding of circuit analysis much clearer, and will make us more powerful to understand the circuits better. Thank you, and see you there.